In my previous lecture, I was discussing about the classification of elements and the periodic properties, and also while giving introduction to type of compounds we can anticipate from main group elements, I gave information about the type of compounds we came across and their classification and their general properties. Once after knowing those things, before we proceed to study in detail the chemistry of main group elements group wise, let us first look into the structure and bonding concepts that are available to explain the bonding, geometry as well as shapes of molecules of main group elements. So, in that context, first ever advancement was made by Gilbert Newton Lewis, and in 1916 he proposed the theory of bonding at University of California at Berkeley, that is called as Lewis dot structures. And he also, besides working on the bonding concepts, he added information about electrons in the periodic table, worked on purification of heavy water, that is D2O, and also he proposed acid base theory, and we are all familiar with Lewis acid base concept. It is one of the fundamental studies as far as the interaction of acid and bases are concerned. Worked in the field of photochemistry, he is also worked in the field of photochemistry, and in fact he was nominated 41 times for Nobel Prize. Unfortunately, he was found dead on 23rd of March 1946 in his laboratory at Berkeley. At that time, he was working with hydrogen cyanide. So, let us look into the Lewis concept, how he came up with some solution to explain the bonding in main group compounds. So, according to Lewis dot structure, what we should do is, we should determine how the atoms are bonded in a molecule. For that one, we have to consider one of the assumption that if there are only one type of elements and multiple copies of another element, the unique element should be considered as central, and then we should look into the counting of total electrons of all the atoms in their valence shell, and if hydrogen is there, it is most of the time it is peripheral and it is bonded to nitrogen, oxygen and sulfur. So, after knowing the basic composition, we should start placing the electrons surrounding the central atom, and we should extend this to peripheral atoms. So, the first step is to determine the total number of electrons that are available. We use the ground group number of an element to indicate the number of valence electrons that it contributes to the molecule. So, this was the assumption that time. So, now the group number does not make much sense, because we are giving group number from 1 to 18. So, group number if you consider, so there will be some problems. What we should do is, instead of going by group number, we should remember the valence electronic configuration of all main group elements. So, example, oxygen has S2P4 electronic configuration. So, the contribution of oxygen towards the bonding is 6, that is S gives 2 electrons and p orbital gives 4 electrons. So, let us look into other concepts that came in Lewis structure. Once we have determined the number of total valence electrons, we can start distributing them throughout the molecule. When we represent electrons, they will be in pairs. Electron pairs can be represented with 2 dots or a solid line. So, let us look into some molecules or ions. Let us consider a simple anion such as ClO2 minus. As a first step, what we should do is, we should count the valence electrons of all the atoms that constitute this ion. So, here we have Cl. Cl has S2P5 electronic configuration, that means we have a total of 7 electrons. Then we have 2 oxygen atoms, each one is giving 6 electrons, as they have S2P4 electronic configuration. So, 6 into 2, what we get is 12 electrons. Since one negative charge is there, one additional electron has to be counted. So, we have a total of 20 electrons. Now, we have to identify the central atom. In this one, central atom is chlorine, and then we have 2 peripheral atoms as oxygen. Now, we know that we need 2 electrons for making a bond. So, this is for making one ClO bond, and this is for making another ClO bond. So, we have spent now 4 electrons. Now, we have to distribute these electrons surrounding these 3 atoms to satisfy their octet. That means, surrounding each oxygen atom or chlorine atom, we should put a total of 8 electrons, that is 4 pair of electrons. Now, we have left with 16 electrons. Now, these electrons we should distribute. Before we distribute these electrons, what we should do is, we should first look into the electronegativity of these 2 atoms. First, we should start satisfying the octet of most electronegative atoms. Since oxygen is the most electronegative, let us start completing its octet. Since we need 6 more electrons to satisfy this one. Now, if you count, we have 8 electrons, the octet of this oxygen is completed. Now, we are left with another 10 electrons, we shall do it for this one here. So, we have used out of 10 6 electrons. Now, we are left with only 4 electrons are there. Now, if we just look into this ion, oxygen has 8 electrons, this oxygen has 8 electrons. Now, this chlorine has only 4 electrons. What we should do is, remaining 4 electrons should be closed here, placed here. Now, if we count, we have 8 electrons, 8 electrons and 8 electrons. So, this octet is satisfied. This is how one can write the Lewis dot structure for ClO2 minus, and that means, in ClO2 minus, octet structure or Lewis dot structure successfully explains the bonding. So, one can write in this fashion also. This is the Lewis dot structure for ClO2 minus. Instead, one can also write in this fashion. Instead of writing 2 dots, one can also write a solid line like this. This also indicates the presence of 2 electrons. So, one can write the structure like this. So, this explains, yes, ClO2 minus satisfies Lewis dot structure, and of course, what would happen if we consider this as a neutral, then there will be short of 1 electron, and if you take, that means essentially by simply doing this electron count and trying to understand the Lewis dot structure for a particular molecule, we should be able to tell whether it should exist in neutral form, anionic form or cationic form. So, let us look into a couple of more examples here. Another interesting molecule is carbon monoxide. In carbon monoxide, we have carbon and oxygen, and in case of carbon, we have S2 P2 electronic configuration. So, we have a total of 4 electron. In case of oxygen, again we have S2 P4 electronic configuration, that is, we have a total of 6 electrons. Now, as usual, we will put CO like this and put a couple of electrons here to establish a CO covalent bond. Now, we are left with 8 electrons. Using 8 electrons, we have to satisfy the octet of oxygen as well as carbon. Since oxygen being more electronegative, let us first satisfy the octet of this one by putting 6 electrons here. So, now we have utilized 8 electrons and we are left with 2 electrons. These 2 electrons should be placed here. Now, if we just look into this CO, octet of oxygen is satisfied, whereas carbon has only 4 electrons, that is, in short of 4 more electrons. What we should do is, we have to think of making it a multiple bond. So, oxygen electrons, either instead of keeping here, we can as well place it here. Similarly, this pair can also come here. As a result, what would happen, the structure would look like this. Now, if we count electron for oxygen, we have 8 electrons, and similarly if we count, we have 8 electrons. So, that means this type of structure gives satisfactory answer to the existence of CO. That means, here one can write carbon to oxygen triple bond, and these whatever the electrons are there, they are essentially makes carbon monoxide a Lewis base with pi acceptor capabilities. So, like this one can look into several examples. So, let us look into some resonance structures. Lewis structures for certain atoms do not match experimental observations. For example, if you look into the bond lengths of CHO2 minus predicted by Lewis dot structure are essentially incorrect. So, according to Lewis dot structure, one CO bond should be shorter, one CO bond should be longer, as one of them has two bonds whereas the other one has double bond. So, when we look into the structure of this molecule, both the CO bonds are identical, that means having the same bond distances. So, here Lewis dot structure does not explain why both the CO bond distances are equal. So, in this case we have to evoke another concept called resonance. Of course, here one can write two resonance structures for this ion. One can write like this, or we can just simply exchange the double bonds. So, this is how it looks like, and the overall structure can also be written in this fashion. So, this is how now the resonance structure agrees well with the structural details that has come, indicating both the CO bonds are equivalent. So, of course, one can keep on writing the Lewis dot structure for whatever the molecules we come across among main group elements, but we have some limitations of using the Lewis model. For example, when we have a molecule or an ion with odd number of electrons, Lewis dot structure cannot really come up with a structure for this one, because always we count electrons in pairs. For example, if we consider nitrogen oxide, we have a total of 6 plus 5 11 electrons in the valence shell. Because of 11 electrons, we should not be able to write an appropriate Lewis dot structure. And again, if an atom may not have enough electrons to complete its octet without having formal charges, that is compounds of group 13 elements, because of S2p1 electronic configuration and capable of forming only 4 bonds, what would happen is we will end up with only 6 electrons like BF3 or BCl3. In those cases, Lewis dot structure cannot explain, despite these compounds are stable to an extent. Another problem with Lewis model is when it exceeds 8 electrons. For example, if we consider molecule SF6, we have 12 electrons, and Lewis dot structure cannot explain how we can arrange these 12 electrons surrounding sulfur atom. And another important failure is predicting the magnetic nature of oxygen molecule. Oxygen molecule is paramagnetic, whereas Lewis dot structure, if you write, it is going to be diamagnetic. Besides all these limitations, the geometry and shape of the molecules cannot be explained using Lewis dot structure. These are the major limitations that led to the advancement or refinement of Lewis dot structure to come up with a better bonding concept. The next bonding concept that was proposed to explain bonding and geometry and shapes of molecules is valence shell electron pair repulsion theory. So, what are the concepts we use in valence shell electron repulsion theory? So, of course, this was proposed by Sidgwick and Powell in 1940, and essentially it uses the valence bond concept proposed by Linus Pauling. And besides Sidgwick and Powell proposing this in 1940, it was refined by Gillespie and Nyholm in 1957, and essentially it involves the counting the number of valence electrons that are present in a given molecule or an ion, very similar to Lewis dot structure. Only the difference is these electron pairs are called, along with the bonded pairs, are essentially called as steric numbers in modified valence shell electron pair repulsion theory. So, we use a term called steric number. This is nothing but the number of attached atom plus number of lone pairs. Assume that the electron pairs around central atom repel each other. The more stable geometry corresponds to the obtained by maximizing the distance between steric points on the surface of a sphere. Before we start, we should also know that in a molecular ion we can have lone pair as well as bonded pair. So, that means when we think of lone pair, bond pair, lone pair and bond pair interaction, the lone pair interaction or repulsion is maximum, and then followed by lone pair bond pair repulsion, and then bond pair repulsion. That means in a molecule, if we have more than 2 lone pairs, we have to spread them as much away from each other as possible, so that the inter-electron repulsion can be minimized and hence the molecule can have some stability. And also lone pairs occupy more space than bond pairs, and as a result you can anticipate larger bond angle between the lone pairs from the central atom. So, let us look into the prediction of molecular geometries using valence shell electron pair repulsion theory. First, we have to draw the Lewis structure, that is the first thing one has to do, and then count the total number of bonding regions and lone pairs around the central atom and arrive at the right steric number. And as I said, again I repeat, steric number is nothing but the number of attached atom plus the number of lone pairs, and arrange the bonding regions and lone pairs in one of the standard geometries to minimize electron repulsion. So, multiple bonds count as single bonding region in VSEPR theory. So, I have shown some of them here. For example, if the steric number is 2, one can think of a linear geometry, and here steric number is given 2, and if the steric number is 3, the geometry will be trigonal planar. If the steric number is 4, the geometry is tetrahedral, and if the steric number is 5, it has to be trigonal bipyramidal, and if the steric number is 6, it is octahedral. I will show you some of those things. If the steric number is 2, this is the linear, it should be something like this. If the steric number is 3, it is trigonal planar, example BF3, BCl3 molecules, it would be something like this, and the angles will be 120 degree between the 2 atoms. And if the steric number is 4, it will be tetrahedral, the angles will be 109.7 degree. It appears like this. And if the steric number is 5, we have trigonal bipyramidal geometry. It will be like this. 3 will be in equatorial at an angle of 120 degrees, and whereas these will be axial ones, it will be something like this. And if the steric number is 6, it is going to be octahedral. Something like this. Here in the plane, all 4 peripheral atoms will be making a 90 degree, whereas axial ones will be at 180 degree, but they will also make 90 degree with each equatorial ones. This is octahedral geometry. Now, let us look into the molecular shapes, and molecular shape information comes only when we have a different bond pair and different lone pair. That means, if all of them are not bonded pair and we have 1 or 2 lone pairs, then we have to look into the shapes of the molecules or ions. So, and when we talk about molecular shapes, two entities comes into picture. One is bond distance, that is nothing but the distance between the nuclei of two bonded atoms along a straight line, and then bond angle, the angle between any two bonds containing a common central atom. For example, you can see here I have shown some molecules, and the one with 4 side peripheral atoms having is this one is a tetrahedral. In this tetrahedral molecules, the bond angles are, this is the bond angle, these bond angles are 109.5, and this is a trigonal planar molecule similar to BF3. Here bond angle is 120, and this is trigonal bipyramidal geometry. Here we have two type of bond angles, one is bond angles in the equatorial plane and the other one is bond angles between the two axial atoms, that is 180, and also between axial and equatorial it is 90 degree, and between the equatorial it is 120 degree. And this one with square pyramidal geometry, none of the main group elements show square pyramidal geometry unless they have a lone pair in one of the axial position. Otherwise, most of the main group elements do show only coordination number 4 and tetrahedral geometry, and when they, especially when we go to heavier elements, because they are capable of expanding the coordination number due to the availability of d orbital, they can show more than 4 coordination number. So, here when the coordination number is 6, all the angles are 90, this is a typical octahedral molecule, and in case of coordination number 7, the geometry is pentagonal bipyramidal, where the angles in the equatorial are 72 degree, and whereas each of this one makes an angle of 90 with the axial atoms. Let us look into some more examples and their geometries. For example, if you look into a molecule having composition AX2, where steric number is 2, it is essentially linear and the angle is 180, and the example is BeCl2. And if molecule is AX3, we have steric number 3, and the predicted geometry for this one is trigonal planar, something like this. I had shown you earlier, the angles are 120 degree, and example I have given here is BF3. Similarly, when you go for AX4, steric number is 4, it is tetrahedral. Example is SiF4, silicon tetrafluoride. So, here it is a typical tetrahedral molecules with angles being 109.5. In case of molecule having AX5 composition with steric number 5, the geometry is trigonal bipyramidal, and as I said, angles are 90 as well as 120, example PF5, PCl5. In case of AX6, steric number is 6, octahedral, again example is SF6. And of course, so far whatever the molecules we discussed, we had only bonded pairs and there were no lone pairs. And let us look into some molecules where we have both of them in different ratio. Let us look into steric number 2, and if we do not have lone pair, then the geometry is again linear, example CO2 and BeH2. If we have steric number 3 and 0 lone pairs, then the geometry is trigonal planar, like examples BF3, SO3 and etc. And if we have 3 steric number and 1 lone pair is there, then the example is SO2 and ozone. For example, you can see we have 2 bonded pairs are there and 1 lone pair is there. All the 3, both bonded pair and lone pair, occupy the planar position. So, molecule will be bent shape, whereas the geometry is trigonal planar. And similarly, when we have steric number 4 and the lone pairs are 0, it is a typical tetrahedral molecule with the geometry tetrahedral and shape is also tetrahedral, example SO4 3 minus or CH4. And when we have 4 steric number and 1 lone pair, this shows the shape as pyramidal, something like this. One of the bond is taken out. So, this is pyramidal, example ammonia and pH 3 and arsenic trichloride. Of course, here the lone pair sits, the geometry is still tetrahedral, whereas the shape is pyramidal, because while considering the shape we are ignoring the lone pair. So, it is pyramidal. And similarly, when we have steric number 4 and 2 lone pairs, then the example is water, hydrogen sulfide, SF2 and I3 plus molecules. So, now I have to take out one more bonded pair. So, now we have one bond pair here, one bond pair here. Geometry is tetrahedral, but in absence of this lone pairs, the shape will be like bent shape or V shape. It is something like this. So, when we have steric number 5 and no lone pairs, it is a typical trigonal bipyramidal molecule. And then when we have 5 steric number and 1 lone pair, it is well known SF4 molecule having seesaw structure. So, in this one the geometry is trigonal bipyramidal, as one of the lone pair occupies one of the equatorial position. So, geometry should be something like this. So, this is how it appears. Another one lone pair is here, and since the lone pair is not, it is a typical trigonal bipyramidal geometry with steric number 5, but if one is lone pair and it has to be placed in the plane, because that makes angle 120. So, when you for the shape, if you just ignore this one, now it resembles a seesaw. That is the reason SF4 molecule we always say that it has seesaw shape. And of course, to keep little more space, it is not exactly a symmetric seesaw, still they little bit bent towards these two, giving more space for these lone pairs. And when we have steric number 5 and number of lone pairs are 2 and bonded pair is 3, then we have T shaped molecule. For example, ClF3 is an example for this one. Same analogy one can use here. For example, we have trigonal bipyramidal geometry. We have trigonal bipyramidal geometry here. So, in this one what we are doing is we are taking out these two and we are placing the lone pair here. If you place lone pair here, now it appears like a T molecule, and one lone pair is sitting here, one lone pair is sitting there. So, the shape is T shape, whereas the geometry is trigonal bipyramidal. Similarly, if we consider steric number 5 with 3 lone pairs and 2 bonded pair, example XCF2, I3 minus and IF2 minus, in this case we have to take out one more lone pair. The shape will be linear, but geometry is always trigonal bipyramidal, and essentially these are 3 lone pairs and these 2 are bonded pair. So, this is how without any problem one should be able to understand the difference between the shape and geometries if we have both lone pair as well as bond pair in case of some of these molecules. And VSEPR theory explains very comfortably the geometries of most of the elemental compounds of main group. That means, valence shell electron pair repulsion theory explains successfully the shapes and geometries of most of the compounds of main group elements. Let us look into some molecules or ions having steric number 6. When you have steric number 6 with no lone pairs, examples are plenty: SF6, PF6 minus, SIF6 2 minus. So, in this case essentially a typical octahedral geometry we can see. When we have steric number 6 with one lone pair, and then we have to take out to describe the shape, we have to take out one axial position, then it will be square pyramidal shape. So, this is our steric number 6. In steric number 6 we have 5 bonded pair and 1 lone pair. So, I take out this one. When I take out this one, now the shape is going to be square pyramidal. For example, IF5, BRF5 have square pyramidal shape. When we have steric number 6 and with 4 bonded pair and 2 lone pairs, what I should do is I should take out this also. Now, we will be having a square planar geometry, a square planar shape, where the geometry is still octahedral, while describing the geometry, we have to include the lone pairs as well. When we are defining the shape, we can ignore the lone pair. For example, XEF4, it has 6 pairs, out of that 4 bonded pair and 2 lone pairs are there. And when you take out these 2 lone pairs, the geometry is still octahedral, whereas the shape is square planar, and same thing is true in case of IF4 minus also. Maybe let us examine in case of IF4 minus whether it is shape is square planar or not. IF4, let us count electrons. 7 electrons are coming from I, as it has S2P5 electronic configuration, and 4 fluorine atoms are giving 1 electron each. So, 4 and plus 1 is here charge. So, that we have 12 electrons by 2 means 6 is the steric number. Out of this one, 4 bonded pairs are there and 2 lone pairs are there. Yes, the prediction whatever we have shown here is correct. So, it has a typical square planar shape, whereas geometry is octahedral. Let us look into IF5. Again, in case of IF5, we have 7 plus 5 equals 12, that is 6 is the steric number, and we have 5 bonded pairs and 1 lone pair. So, the shape is square pyramidal, whereas geometry is octahedral. So, prediction is correct. Let us look into IF7. In case of IF7, we have 7 from iodine S2P5 and 7 fluorine atoms are giving 7. So, we have 14 electrons, that is steric number is 7, and here all are bonded pairs. So, geometry is pentagonal by pyramidal. Okay. So, pentagonal by pyramidal. So, this is how we can arrive at the structure as well as the shape of any molecule from main group compounds. Let us look into the valence bond theory. In valence bond theory, we use the concept hybridization. So, that means the space generated due to the overlapping of orbitals has a maximum capacity of accommodating not more than 2 electrons with opposite spins, that we should remember. If the overlapping is greater, the bond is stronger and is more stable. Bond strength essentially depends on attraction of the nuclei for the shared electrons. When 2 atoms combine to form covalent bond, the valence orbitals present in each atom overlap to form new hybrid orbitals with different shape from the original. That means, basically if we are considering the orbitals such as S, P, D or F from which they are made up of, the hybrid orbitals will be having a totally different shape from the original orbitals from which they have been constituted. So, for example, let us look into sp hybridization, and in this case I have shown some structure here. So, basically what happens, carbon, if you consider carbon having S2 P2 electronic configuration. So, if it undergoes sp hybridization, what we need is we have to consider only S. Before that one, S electron has to be promoted. So, at this stage what we are doing is we are not mixing all the 3 p orbitals along with S, we are considering only one of the p orbital along with S. That means, what we need is one S orbital, one of the p orbital, and now they will combine together form 2 sp orbitals. Out of 2 sp orbitals, what would happen is this is an example in case of acetylene. So, we consider this is carbon. So, this is one orbital, they are interacting with each other. So, another one is utilized for making bond with hydrogen. Now, we are left with these two p orbitals which have not participated in hybridization. So, they are orthogonal to each other. So, we have these, and similarly we have two more p orbitals from both the carbon atoms. So, this is called pi bonding. So, we have a total of 1 sigma bonding and 2 pi bonding, and between two carbon atoms, and between hydrogen we have 1 sigma bonding. So, this is how you can explain the bonding using hybridization concept. Let us look into some more molecules here. So, let us consider boron atom. In boron atom, electronic configuration is I have already given here. You can see electronic configuration is S2P1 in the ground state. Prior to the hybridization, what would happen is it will promote the S electron to the P to have S1P2 electronic configuration, and now the hybridization of S and 2 p orbital takes place to give 3 sp2 hybrid orbitals, and these 3 sp2 hybrids will be disposed at an angle of 120 to each other, something like this. You can see these 2 p orbital and 1 s orbital is participating in hybridization, and we have these 3 are sp2 hybrid orbitals. Now, they interact with the 3 fluorine atoms to generate BF3 molecule, and the angles are 120 degree between 2 fluorine atoms at the center. And another examples include CO3 2 minus, it can also be an example for H2CO or ethylene and NO3 minus and etcetera. We come across numerous examples for this sp2. Similarly, we can look into another hybridization concept. So, here let us look into the sp3 hybridization, how it takes place. Of course, ideal example is considering methane, and in carbon we have S2P2 electronic configuration. So, during hybridization, one of the S again promoted to P to have S1P3 electronic configuration, and that means here one S orbital will combine with 3 p orbitals to form 4 sp3 hybrid orbitals for bonding. Compounds involving sp3 hybrid orbitals are CH4, carbon tetrabromide and etcetera, and also PH3, NH3, H2O, all are examples for sp3 hybridization. Only in case of NH3, what would happen is we have 4 sp3 hybrid orbitals, but one with 2 electrons. For example, let us consider NH3. Here the electronic configuration of N is S2P3. Again, prior to the formation of NH, S and P are combined together. So, before that one combined together to form 4 sp3 hybrid orbitals. When it makes 4 sp3 hybrid orbitals, something like this. So, 3 will have 1 electron, whereas the 4th will have 2 electrons, because we have a total of 5 electrons are there, 2, 3, 4, 5. So, now we have 4 sp3 hybrid orbitals with 3 having 1 electron each, and 1 sp3 has 2 electrons. So, when we interact this one with hydrogen, they arrange in this in a tetrahedral fashion, and this will remain intact with 2 electrons, and other one will interact with hydrogen to form 3 NH bonds, and here these 2 electrons will make it the Lewis base, and this one has a pyramidal shape if you are ignoring the lone pair, and the geometry is still tetrahedral. And of course, in case of water it is even interesting. Again we have S2 P4 4 electronic configuration, that means we have total of 6 electrons are there. When we combine s and p orbitals together to generate sp3 hybrid orbitals, we will be having a situation like this, in which 2 sp3 orbitals will have 1 electron each, whereas remaining 2 sp3 orbitals will be having 2 electron each. So, now only those sp3 having 1 electron can combine with 1s1 of hydrogen to form 2 OH bonds, and other 2 will remain intact. So, that means this indicates oxygen has 2 lone pairs and 2 bonded pair, and the geometry is still tetrahedral, whereas the shape is bent shape or V shape we call it. So, this is how hybridization concept can be used along with valence shell electron pair repulsion theory to explain the bonding in main group compounds very efficiently. You can see here now in case of sp3 all the 4 orbitals are participating. So, these 3 p orbital and 1 s orbital will combine together to generate this 4 sp3 orbitals, which are disposed at an angle of 109.5 degree with respect to each other, and they interact to form a typical tetrahedral molecule. Similarly, one can explain in case of ethane also. Ethane also hybridization is essentially sp3, and it is not ethane, it should have been ethylene. In case of ethane it is sp3, in case of ethylene it is the carbon has undergone sp2 hybridization, and we have sp2 orbitals are there, 2 of them on each carbon will be making bond with hydrogen, and the one of the sp2 from both will interact to make carbon carbon bond, and then we have 1 p orbital left on each one with 1 electron, they make pi bond. Okay, let us look into some questions here related to both valence electron pair repulsion theory as well as valence bond theory or hybridization concept. So, now explain, I read the question, explain why x p x bond angles for the series POX3. POX3 is a typical tetrahedral molecule, decreases from x equals, we have POBr3, POCl3 and POF3. If we consider when x equals Br, the angle is 104.1, when x equals Cl it is 103.3, whereas x equals F it is 101.3. Why bond angles are shrinking as we go from POBr3 to POCl3 to POF3. So, of course, here we should remember the fluorine is the most electronegative halogen. So, it will draw electron density in the PF bond away from P. So, P is the central atom here. The structure is something like this. Okay. So, in this one fluorine, if it is fluorine is the most electronegative halogen. So, it will draw electron density in the PF bond away from P. Repulsion of the PF-PF bonding pairs will be less than the repulsion of PCl and PBr bonding pairs. So, FPF bond angle will be the smallest. And another way also we can explain, I will come to that one in a couple of minutes. Let us look into another example of water and hydrogen difluoride. For example, let us consider H2O and F2O. Of course, both are bent molecules with oxygen having 2 lone pairs. So, the question is between H2O and F2O, which will have larger angle, which one will have larger angle. So, now again fluorine is more electronegative than hydrogen. Therefore, the space occupied by the OH bonding pair in the oxygen valence shell will be much greater. Hence, H2O will have the larger XOS bond angle. As I said, this can also be explained, that is based on the electronegativity of two atoms that make a bond, we can write these molecules in three different ways. Let us see, this is a central atom. Okay, if we remember these three, of course, here we have some okay. So, whatever the bond angles we have to discuss, we have to see that it falls into one of these three categories. So, here this is central atom is here and two peripheral atoms are there, and if the electronegativity of central atom is much greater than peripheral atoms. So, what happens basically, the bonded pair will be much towards this one. As a result, what happens, bond electron density increases here. So, in order to release that repulsion, the bond angle enlarges. Okay. So, whereas in this case where the electronegativity of central atom as well as peripheral atom is comparable, then probably we can think of the bond angle coming very close to the typical tetrahedral angle. If the electronegativity of the peripheral atoms is much larger compared to the central atom, in this case what happens, the entire electron density is pulled towards this one. As a result, electron density at the central atom diminishes, as a result bond shrinks. Okay. If you just remember these three basic principles, one should be able to explain the bonding, the trends and all those things without any difficulty. So, another aspect one should remember is Bend's rule. That means, what is Bend's rule? The Bend's rule says more electronegative substituents prefer hybrid orbitals having less S character and more electropositive substituents prefer orbitals having more S character. I repeat again, according to Bend's rule, the more electronegative elements prefer an sp3 orbital having more p character and less s character. On the other hand, less electronegative atoms, when they are binding to the central atom, they prefer a hybrid orbital having more s character and less p character. So, that means this, if we consider the examples of CH4, CF4 and CH2F2, we can explain these things very readily. If we consider CH4 or CF4, it should not be a problem. Here the electronegativity of central atom or peripheral atom does not come into picture, because it has to be a symmetric tetrahedral molecule. Angles would be essentially same, and where the angles in CH4 is same as essentially the angles in CF4. But when we consider CH2 F2, so what would be the angles? That means we can think of two types of angles. Now, we should be able to tell what is the angle now. The CF bonds are formed from sp3 plus X hybrids. Okay. That means with slightly more p character and less s character than a typical sp3 hybrid orbital, because when we consider 4 sp3 hybrid orbitals, we should remember that we are using 1 s and 3 p. As a result, each sp3 hybrid orbital will have about 25% s character and 75% p character. But when highly electronegative elements are combining with an atom, so they prefer to have an sp3 hybrid orbital having more p character and less s character. So, in this case what happens, the electron density and in that case bond angle essentially shrinks. Okay. It is very easy to understand that one. For example, if we just look into the mutual orientation of 3p orbitals, they are at 90 degree to each other, px, py, pz, and s orbital when it combines with them, the sp3 hybrid generated will have an angle of 109.5 degree. But if the s character slowly diminishes, what happens, we will be only looking into the p orbital, and as a result one can anticipate decrease in the bond angle. So, that can see here the bond angle decreases, whereas in case of hydrogen these CH bonds will carry an sp3 having more s character. As a result, what happens, the bond would enlarge. So, bond is going to be enlarged, and this can also be analyzed in another way that I just described. For example, something like this will be the situation here. The electron density is pulled more towards fluorine. As a result, what happens, the bond angle shrinks, and whereas here electron density is still close to the carbon. In you know that in carbon, in methane or such molecules, carbon carries -4 oxygen state. So, in this case what happens, since more electron density is going towards carbon, this bond angle increases. So, that means even Bend's rule we should be able to explain conveniently using some of these concepts, either Bend's rule or simply analyzing where electron density is there and where the bonded pair is moving. One should be able to analyze and say what are the bond angles, all those things. So, let us consider a CO2. Of course, MO diagrams are much more clearer in giving and defining all the properties of whether it is main group elements or transition elements. To draw MO diagrams involving 4 set of orbitals, we have to consider 3 sets of atomic orbitals and 1 set of molecular orbitals. In case of CF4, we have to consider 5 sets of atomic orbitals and 1 set of molecular orbitals. Similarly, in case of SF6, 7 sets of atomic orbitals and a set of molecular orbital have to be considered. This makes MO diagrams more complicated and difficult to both construct and interpret, but is there any simple way to do that one? So, let us look into some examples of MO diagrams that we are familiar with main group compounds. I have shown here for carbon monoxide, when we are placing the atomic orbital, we place it in such a way that the most electronegative elements, atoms, atomic orbital will be much lower in energy relatively compared to the other atom. If you are considering homodiatomic molecule, it should not be a problem, both are having the same energy, but if you are considering a molecule like CO, NO and other things, due to the difference in the electronegativity, those which have higher electronegativity should have lower energy. So, here this 2s orbital is much lower in energy, and similarly these 2p orbitals are much lower in energy compared to the 2p orbitals of carbon. So, now you can simply make these 2 sigma bonds and this is pi bond. So, this is how the total of 6 plus 4 electrons whatever we have, we can arrange in this fashion, and this is for HF. In case of HF, you can see here this is essentially non-bonding, because 2s of F is not combining, this remains non-bonding, and whereas here remaining 6 electrons, 5 electrons, because S2 P5 electronic configuration, these 2 electrons are not participating. So, they remain as non-bonding, whereas remaining 5 electrons of 2p, 4 will always remain non-bonding, and 1 electron from this one and 1 of 1H will combine together to form the sigma bond. So, this is how you can explain the bonding in HF using simple molecular orbital diagram. Okay. And one can also use the same analogy to explain bonding in difluorine F2 molecule. For example, here 1s will give bonding and antibonding for electrons, no problem. So, here 2s combine to generate sigma bonding and antibonding, 4 electrons are there. Now, remaining here 5 electrons from here and 5 electrons from here can be placed conveniently here in sigma 2 in pi 4 electrons and in the pi star about 4 electrons. You can see here we have in the pi star 4 electrons are there, and this is how one should be able to write MO diagrams for diatomic or triatomic molecule. One can also make an attempt to write such MO diagrams for even as simple as N2 and O2. When you write for O2, you can predict 2 unpaired electrons are present, showing that it is paramagnetic. Let me stop at this stage of structure and bonding discussion. In my next lecture, I will be focusing your attention to the chemistry of hydrogen, and after completing the chemistry of hydrogen, I would start discussing the main group chemistry, considering one group at a time.